This grant is funded by the United States Environmental Protection Agency through the Texas Commission on Environmental Quality. This video is intended for educational purposes only. Any mention of trade name, commercial products or services does not constitute endorsement or recommendation for use. Water Quality Guide, a series of videotapes about water quality problems that affect the safety and acceptance of the public water supply. These presentations are made by operators and intended for use by operators. Each videotape covers symptoms, causes, and solutions. Small water operators are expected to give their customers clear and colorless water without noticeable odor or taste, right? However, colored water is a rather common problem. It's the operator's job to correct this problem before it gets to the consumer. More often than not, iron, manganese, organic matter, iron bacteria, or some combination of these contaminants cause colored water problems. Not only do these materials cause the water to look bad, but taste and smell bad too. The symptoms of iron and manganese problems are colored water complaints, red or brown stains on fixtures and clothing, high chlorine demand, and sediments in tanks and lines. Closed valves won't open, and open valves won't close. In some cases, well screens, treatment units, and pipes get clogged. But the worst problem occurs when a main line break stirs up deposits in the distribution system. Sediments break loose, ending up in bathtubs, sinks, dishwashers, and washing machines. The sheer volume of colored filth can be astonishing, and the number and intensity of complaints that follow staggering. Red and black slimes are another symptom. In this case, the culprit is iron bacteria. These non-pathogenic bacteria oxidize iron and manganese, resulting in slimy reddish-brown deposits. When customers see or experience these symptoms, they know that something's wrong. Iron is generally thought of as a metal, but it's also a common mineral in the soil. In the water supply, either iron or manganese can be obnoxious, even at low levels. On a positive note, these minerals are not dangerous to health at levels found in the drinking water. The state has set the secondary standard for iron at 0.3 milligrams per liter, and for manganese at 0.05 milligrams per liter. Meeting these standards should prevent objectionable color, taste, and stains. It is common, however, for complaints to start at lower levels than the standards. Iron and manganese get into the water because rainfall dissolves and carries these minerals down into water-bearing formations. Corroded iron pipe, rusting tanks, and stagnant water mains are additional sources of iron from within the water system. Iron and manganese can be observed in several forms. From wells, iron and manganese are usually in the dissolved form. Scientists call this ferrous and manganese ions. More commonly, it's called clear water iron because it's colorless. When well water turns from clear to yellow, red, or brown after exposure to chlorine, that shows the well water contains clear water iron. Exposure to air or chlorine causes dissolved iron and manganese to turn into solid particles. Initially, these particles are too small to see or settle. At this stage, the tiny particles are suspended in the water, making it look colored and cloudy. If left alone, these particles slowly grow large enough to settle, depositing red, orange, brown, and sometimes black sediments. Organically bound iron can result when the iron combines with certain organic ions, making it much harder to remove that mineral iron. Luckily, our water supply doesn't have this problem. By far, the most obnoxious form of iron or manganese is bacterial. Iron bacteria causes slimes, deposits, plugged well screens, taste and odors, and high chlorine demand. These bacteria are very resistant to chemical control. They protect themselves with a heavy coating of iron minerals around each tiny cell. They are tenacious, coming back even after being burnt out with high levels of chlorine. These uninvited microbes must be continually monitored to keep them under control. After a red water problem is reported and confirmed, the nature and extent of the problem must be determined. This requires collecting samples and determining the amount and type of color-causing contaminants. Start with a simple field test, which involves collecting a 1-liter sample from the well discharge. part of the sample is oxidized by adding 4 drops of bleach. After mixing by shaking the sample, the chlorine turns the dissolved clear water iron, or manganese, to its colored particulate form. Samples of the untreated water and chlorinated water are then filtered through a membrane filter. Sure enough, the problem comes to light. The color difference between the 2 filters provides visual indication of the nature and extent of the problem. For more accurate analytical results, collect more samples and send them to a lab. The lab tests for dissolved iron and manganese, as well as color, turbidity, and total organic carbon. From the laboratory results, the concentration and type of color-causing contaminants are revealed. This information assists the operator in selecting and implementing a process to control the colored water problem. The water system manager needs to thoroughly understand the colored water problem before selecting a treatment option. The cost can be a problem. The equipment and chemicals can require a substantial initial investment and long-term commitment. Plans should be prepared by a registered professional engineer. The state needs to review and approve the plans before starting construction. It took about a year to complete the testing, planning, and construction. Water systems usually use one of 5 methods to control their iron and manganese problems: sequestering, oxidizing filters, pressure aeration followed by filtration, continuous chemical oxidation followed by filtration, and ion exchange softening. A big concern is to keep the customers happy with the water they receive. When iron and manganese are found at relatively low concentrations, less than 1 milligram per liter, and in the dissolved form, sequestering with a phosphate compound is a common treatment option. Sequestering is not effective for iron bacteria or after oxidation has started. Sequestering works best when the pH is near 7, but below 8 is okay. Sequestering does not remove the problem materials, it just carries them along with the water. For moderate levels of dissolved iron or manganese, up to about 10 milligrams per liter, water system operators should consider using an oxidizing filter. The filter media is a manufactured resin or manganese green sand coated with manganese oxide. The filter media traps and oxidizes the problem metals. Dissolved oxygen must be present, and periodic backwash and regeneration is required. For moderate to high levels of mineral iron, aeration and filtration is a treatment option. Pressure aeration for sufficient contact time followed by a multimedia filter removes the oxidized particles of iron. This option is most effective when the pH is above 8 and the water has sufficient alkalinity. Iron bacteria and organic complexes interfere with this process. For more difficult problems involving organic complexes, iron bacteria, and high concentrations of manganese, chemical oxidation followed by filtration is necessary. The oxidizing chemical, usually chlorine or potassium permanganate, is injected into the water as it leaves the well. pH adjustment may also be necessary. A 30-minute reaction time or longer for organic complexes is required to oxidize the undesirable iron and manganese compounds. A filter then removes the oxidized particles. Another treatment option that is practical only for the smallest water systems employs ion exchange. An ion exchange softener can remove low to moderate levels of iron along with hardness. Softening increases the sodium content of the water because sodium is released from the ion exchange resin as iron manganese and hardness are removed. Consider this option only when the combined amount of dissolved iron and manganese is below 5 milligrams per liter. This video will cover only 2 of these treatment options: sequestering and chemical oxidation followed by filtration. Scientists say that 80% of the water systems that have colored water problems find less than 1 milligram per liter of iron and manganese in their water. When levels are in this low range, phosphate treatment is a cost-effective option. Most managers like to keep the costs down. Here are 3 more reasons why this is a preferred treatment option. First, nothing is removed from the water, so there's no wastewater, sludge, or sediment. Second, the equipment is simple, easily replaced, and its operation is uncomplicated. It doesn't take a lot of time to keep it running. Third, phosphates also help to reduce corrosion problems. Phosphates work by binding with undesirable materials and carrying them with the water. In this stabilized form, iron and manganese are not available to react with oxygen or chlorine. Yellow, brown, and red color problems are avoided. Phosphates are expensive chemicals, and management says don't overfeed. Run jar tests to evaluate different phosphate compounds and determine the most effective dosage. Then, carefully adjust and control the level of phosphate in the water. There are some drawbacks to phosphate treatment. Since iron and manganese are not removed, any metallic taste caused by these materials remains in the water. Most customers don't notice the phosphate, but some say the water has a slick or soapy feel. Heat and time break down the phosphates, resulting in the release of iron and manganese into the water. Therefore, use a phosphate that has a good staying power. The equipment for feeding phosphate chemicals is relatively simple. It consists of a tank to store the liquid phosphate solution, a chemical feed pump, tubing, and an injector. Consult with a qualified professional to select a cost-effective phosphate chemical among the many possibilities and to determine the correct feed rate. The phosphate specialist will help select an effective phosphate and explain how to avoid over- or underfeeding chemicals. The sequestering agent must be injected at the proper location. The goal is to inject and mix the sequestering agent before any oxidation occurs. To achieve this, the injection point should be close to the well discharge and at a point of high turbulence. Static mixers or turbine meters downstream of the injection point help promote good mixing. Once the phosphate dosage has been established, the chemical feed pump must be set to deliver the right amount of sequestering chemical. Check this by measuring the gallons of chemical used each day. Record the amount of water pumped from the well each day, then calculate the gallons of chemical used per million gallons of water and compare this number to the recommended feed rate. Use a drawdown tube to accurately set the stroke and speed of the phosphate feed pump. Contact with chlorine oxidizes any iron or manganese that is not tied up by the sequestering agent. Therefore, the phosphate should be added continuously at the established dosage. Set the chemical feeder with a short stroke and high speed to achieve the best contact with the problem metals. A peristaltic pump works well in this application. We then calculate the gallons of chemical used per million gallons of water and compare this number to the recommended feed rate. Once the feed system is set properly and running smoothly, the measured level of iron and manganese at the customer's tap will equal the level from the well. This indicates that problem metals are not deposited nor released and that no oxidation is occurring. The sequestering equipment is doing its job. For moderate to high levels of iron and manganese and to control difficult removal problems, chemical oxidation followed by filtration is often used. The advantages of this treatment option are: problem metals are nearly completely removed, the operator has greater control over the treatment process, a variety of colored water problems can be managed, and sequestering agents don't end up in the customer's water. With this treatment option, dissolved iron and manganese and organic complexes are oxidized with chlorine or potassium permanganate. Once oxidized to the particulate form, filtration removes the offending materials from the water. Oxidation is more effective at higher pH levels. A pH above 7.5 is best for iron oxidation, and above 8.5 for manganese oxidation. There are drawbacks to the chemical oxidation treatment option. Strong, potentially dangerous, and expensive chemical oxidants must be stored and continuously fed. Since iron and manganese are removed, the water system must dispose of a waste stream and get a permit for any discharge. Operators must backwash effectively to clean the filters. Coagulants may also be needed to help the filters reduce the turbidity to acceptable levels. The equipment used at this water plant accomplishes oxidation and filtration in 3 steps. Because a high level of dissolved manganese is the major problem here, the first step is to raise the pH to accelerate manganese oxidation. The water from the well passes through a bed of calcite and Corosex to raise the pH. Calcite, which is mostly calcium carbonate, and Corosex, which is mainly magnesium oxide, slowly dissolve, raising the pH to the desired range. Once or twice a year, more calcite and Corosex are added to the bed. Iron, manganese, and hardness may precipitate out and cement the bed. Regular backwashing is required to keep the bed open. The next step is to feed a 2 to 3% potassium permanganate solution to oxidize iron and manganese. When the well pump starts, the chemical feeder doses permanganate at the required level. It takes less than 1 part per million of permanganate to oxidize 1 part per million of iron or manganese. The last step is to filter out the small particles of oxidized iron and manganese. This filter uses manganese green sand and anthracite. The green sand acts as a buffer for the potassium permanganate. If too much permanganate is fed, the filter media absorbs and holds the excess. If insufficient permanganate is fed, the coating on the manganese green sand continues to oxidize iron and manganese until the coating is depleted. A number of routine tasks help to keep the system operating properly. Each day, carefully check the equipment, record and evaluate water production and chemical use. Filters are backwashed to the pond based on either pressure loss or run time. Periodically, run a filter test on the raw and finished water. Also, check the finished water for any pink color. Pink indicates that the potassium permanganate feed rate is too high. About once a month, refill the feed tank and make up fresh permanganate feed by mixing and dissolving the purple potassium permanganate crystals in the tank. The water produced by this 3-step process looks and tastes a lot better than the untreated well water. The process effectively removes iron and manganese, raises the pH to minimize corrosion, and reduces turbidity to low levels by filtration. Customers are happy, and there are a lot fewer complaints. This video reviewed the symptoms and causes of colored water problems. The forms of iron and manganese, including dissolved, particulate, bacterial, and organic complexes, were explained. The importance of laboratory testing was reviewed, and a field filtration procedure for evaluating the nature and extent of the problem was shown. 5 ways to control iron and manganese problems were briefly summarized. 2 common control options, sequestering and oxidation followed by filtration, were presented. The equipment was shown, and the operating principles were explained for each. Finally, one very important reminder. This brief video provides only an overview of the symptoms, causes, and solutions of colored water problems. If these problems occur, use all available resources to thoroughly understand and address each particular situation.